All right, for this last section, we're going to be looking at real numbers. Any number that is not rational is called an irrational number. So just a little reminder that in order to be rational, what we've been talking about is that they can be written as terminating or repeating decimals. So an example of something that would be irrational would be something like, I'm going to try and write a decimal that will have a sort of pattern but won't actually repeat. So how about this? We'll do 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. So you can see each time I'm going to add another digit, 1, 2, 3, 4, 5. So that would be 6, and it's going to continue. So it kind of has a pattern, but it's not a repetition of any kind. So it's going to keep doing this forever. And so there's going to be no way that we can write this as a rational number, as a ratio of two integers. And so we call that irrational. Now the real numbers are the union, which means all together, the set of the rational and the irrational numbers together. And every real number can be represented as a decimal and corresponds to a point on the number line. So we're kind of putting together all the number sets that we have been talking about this whole semester and putting them all together as this big chunk called the real numbers. Now, a few other ways that you might see an irrational number is in the form of square roots. So we have regular square roots where the definition of that is it's a non-negative number a such that x squared equals that a. Well, you're more used to probably seeing the principal square root, which has that radical notation, and that's just the positive root. So what I mean is if I go down here to this example, it says the square roots of 25. So that's saying some number squared makes 25. Well, that number could be 5 since, of course, 5 times 5 is 25. But that number could also be negative 5 for the same reason. Negative 5 times negative 5 equals positive 25. And so these would be the two square roots of 25. So sometimes we might even write that as plus and minus 5. Now, if you see the second notation with the actual radical symbol written, it only wants the positive of those two. So the square root of 25, we say, is 5. And it's common just to say square root and not principal square root, but that's what's implied when we see that notation. Now the square root of negative 16, this doesn't make sense because there's no number times itself, no real number, that can multiply to a negative. So this is going to be not a real number. And we actually have another part of our number system that includes imaginary numbers, but we won't get into that. When we look at the next one, now we're talking about a different root. So an nth root of a number is denoted with a little symbol n right inside that radical. Now square root is so common that we don't write it, but really it's like with a little 2 on that little part, which is called the index. So again, that number 2 is called the index or the root. And so what it's saying is we need to have some number times itself that many times to make our inside number. So if we look back down at that cubed root of 8, this is saying what times itself 3 times. So something times something times something is going to get me the 8. Well, that something is going to be a 2, since 2 to the third power equals 8. When we're looking at the next one, this is a cube root. Now you guys see a negative number there, and a few moments ago when we were talking about the square root, we said that that was not a real number. That's only for an even numbered index, because you can multiply something an odd number of times and make a negative. So again, we're saying what times itself 3 times makes this time negative 8. Well, that would be a negative 2, because a negative number an odd number of times makes a negative number. So we have negative 2 there. So these are all square roots and nth roots that work out nicely. They don't always work out so nicely, and if they don't work out nicely, we actually call them irrational numbers. So let's take a look at something that might be familiar, the Pythagorean theorem. It's a theorem that relates the sides of a right triangle. So it says if you take a squared, which is one of the legs, and then you take b squared, which is another one of the legs squared, this is supposed to equal the hypotenuse squared, and this works all the time. And so what happened when numbers were kind of being created, the idea that you can have a radical that was, or a number that was not rational, was a new idea. And it was actually found by looking at this Pythagorean theorem. So if you look at the next page, what happened was they said, okay, well, let's make a triangle that has side lengths of 1. So I'm going to look at my number line and draw from 0 to 1, and then I'm going to go up that same distance. So this has length 1, this has length 1. And so what they found was the hypotenuse length was a number that they couldn't exactly explain. It wasn't a real or a rational number. So what I just formed right now is a right triangle. And so Pythagorean theorem says if you take one of the legs squared plus another one of the legs squared, that's supposed to equal the hypotenuse squared. So A is equal to 1, B is equal to 1. And so if we want to find that C, that distance, we're going to have 1 plus 1 equals C squared, 2 equals C squared. So this is saying, okay, we need some number that when you square it, you get 2. In other words, it's asking for the square root of 2. And so the square root of 2 didn't make sense. There was no number times itself that could make 2 any number that they knew. And so it created this whole new other part of math, really. It created the irrational numbers. This was irrational. It wasn't a number that could be written as basically a terminating decimal or a repeating decimal. And so this distance here, which we can visually see, is equal to the square root of 2. So the picture down below, it goes even further to find some more of these irrational numbers, these roots that just cannot be simplified. And this is called the wheel of Theodorus. And it's a very kind of cool visual way of being able to see these radicals, which we don't know exactly, we don't know what rational number they're equal to. So we start out, again, it starts by saying, okay, this side is 1 and this side is 1, which is the exact picture we saw up above. They did write square root of 1 here instead of a 1, but that is equal to 1 still. And so we end up that we have this length, square root of 2. We can like see what square root of 2 is. Now, if we take that and we go up another unit, a whole 1, look at what we have. We have the square root of 2 is 1 leg. We're going to square that. We have that side squared. And so if we want to find out what that hypotenuse is, which you can see in the picture is radical 3, let's see how that works out with Pythagorean theorem. That's going to be 2 plus 1 equals C squared. So we have 3 equals C squared. So C is the square root of 3. So you can see that length. And then again, it continues on. And it puts in a 1 up. So we have that radical 3 squared plus 1 squared equals C squared. So 3 plus 1 equals C squared. 4 equals C squared. So C equals square root of 4. But that's actually a real rational number because that's equal to our number 2. And so one cool thing, if you recreate this with a ruler, what you find out is this is working so beautifully that if you measure out this line segment here, it's going to be equal to a 1 and a 1. You can kind of see that from the picture. And you can see that the square root of 4 is 2. Like you can actually measure that out. Now another thing that you can do if you want to actually put these irrational numbers onto our number line, I'm going to go back up above for a second, is you can actually take this hypotenuse to be like the radius of a circle. And so if you imagine this being dropped around, okay, we don't have to draw the whole circle, but what happens with a circle is that the radius is the same all around, and so it ends up that we have just marked on our number line where the square root of 2 is. And we can do this for each of our radicals that you see in the picture below as well, so it marks a spot for our radicals. The picture also shows that like square root of 4 is between radical 3 and radical 5. Or even better, that if you're asked what is radical 3? Radical 3 is approximately, well, it's between the square root of 4 and square root of 1. I put it between the radicals that we know. And so if this is 2 and this is 1, what we know is that radical 3 is between 2 and 1. And it's a little bit closer to radical 4, so it's probably going to be like 1.8 something. But you can double check on a calculator. If you look up the square root of 3, it's on a calculator, it's estimated to be about 1.73. And again, that's an estimate because this is not going to be written as a terminal decimal. We're going to continue with the idea of estimating square roots. So again, if I look at the square root of 2, I know that that is less than the square root of 4, and it's bigger than the square root of 1, which means with regular whole numbers, I know that the radical 2 is between 1 and 2. Now that's great, but is there a way to get a little bit better approximation? Well, there's something called the squeezing process, where we kind of guess and we're able to kind of narrow down or squeeze down the range of numbers, because between 1 and 2 there's a lot of numbers going on. So one thing to notice is that, okay, if it's between 1 and 2, let's look at what 1.4 squared is. 1.4 squared is about it is equal to 1.96. And so if I look at that, I know I'm getting really close to the number 2, which is what my goal is. So then what about if I look at 1.5? Well, 1.5 squared is 2.25, so that's a little bigger. So what we've done now is narrow down the interval. Radical 2 is between 1.5 and 1.4, and that's again because 1.4 squared, radical 2 squared, 1.5 squared, our numbers are going to be a 2, 2.25, and again 1.96. So we can see that if all of these guys right here are is a true statement, then if you're going to look at their square roots, that's going to be a true statement also. So then let's see, can we narrow it down even more? So square root of 2, let's see, it's going to be, this 1.96 was a little closer to 2 than that guy. So I think I'm closer to 1.4. So let's look at what 1.4, you could try 1 or 2, I don't know, let's do 1.42. If you square that, that's going to be about 2.016. So we've gotten really close to 2. And let's go the other way then. 1.41 squared, that's 1.9881. So that's really getting closer to 2. So what I can say is that radical 2 is between 1.42 and 1.41. So we've come up with a pretty close approximation that it's going to be right between those two. So like 1.415 if you want. Now on a calculator, radical 2 will be approximately 1.4142. So that's a pretty close estimate using this squeezing idea. And again, we're just testing out, and you can use your calculator to find some of these square numbers, but we want to try and find out numbers that are getting us close to 2, which those are. So besides estimating the square roots, just one other thing that we can do is just simplify a little bit. So even if you can't pull out a square root perfectly, like when we say square root of 25 is 5 or square root of 49 is 7, the square root of 360 does not come out perfectly, but there is a perfect square in there. This is actually equal to the square root of 36 times the square root of 10. Like we can actually separate that and take the square root of the number that we know. So this has been now simplified. We do the same thing with the square root of 40. Again, it can't come out as a whole, but I see a perfect number sitting in there, square root of 4. And so that's going to be 2 square roots of 10. When we look at the 24, that one is not so clear to me. I see that it's 24 and 10, but those aren't perfect squares. So then I try and break that up more. I'm trying to find some perfect numbers in here. Nothing's coming. Let's see. Oh, wait, there was a 4. And then 2 and 2 is another 4. So actually for each of those, let's rewrite this. I really have a square root of 4, a square root of 4, and then a square root of, what's left over? We have a 3 and a 5. So that would still be 15. So that's 2 times 2. Those both get to come out, which is going to be 4 square roots of 15. Now the last thing is just putting together all the properties that we've talked about, and the properties have been, we've individually looked at them for our whole numbers and for our integers, and then they work for our rational numbers as well. So putting that all together with our real numbers, we have our closure property that if you add two numbers that are real, it's going to be a real number. If you multiply two numbers that are real, it's going to be a real number as well. So we're staying inside this real number system. The commutative properties work for real numbers. So if you add a and b together, that's the same as adding b and a. If you multiply a times b, that's the same as multiplying b times a. So that commutative property is working. Associative property works. Again, all these a, b, and c, they're real numbers. So if we rearrange the parentheses here, it's still equal when we multiply and also when we add. The identity property says that if you add a number 0 to a real, or add a number to 0, that's just going to be that real number back. And you could do it both ways, really. With multiplication, if you multiply by 1, you get that number back. Again, it can work either way. Those are identity properties. The inverse property, if you add the opposite, you will get 0. And it works the other way, negative a plus a equals 0 also. We have the distributive property going on, again, a, b, and c being any real number, and that includes all these new radicals we've been talking about, and it works with addition and subtraction. The multiplication property of 0 says if we multiply any number by 0, we get 0, and that works again either way. And the last one, the density property for real numbers, really just says that anytime you're looking at two real numbers, there's always going to be, this is a fancy way to say there exists, some number c, that c is going to be between them. So anytime you have two real numbers, there's going to be another real number between them all the time. That's the density of real numbers. And that's it.